Imagine looking up at the night sky and realizing that almost everything you see is temporary. Not just the stars above you, not just the sun, not just Earth, the moon, or the familiar planets moving quietly around us, but the entire age of light itself. The universe can feel eternal because it is so large that our minds cannot touch its edges. Galaxies drift for billions of years. Stars burn longer than civilizations can remember. Black holes seem almost impossible to destroy. And, from where we stand, on one small planet beside one ordinary star, the cosmos looks like something that has always been here and will always continue. But that is not what the evidence tells us. The universe had a beginning. It has changed. It is still changing, and, in a very real sense, the brightest part of its life may already be behind it. Before we begin tonight, if you enjoy calm journeys through space, take a moment to subscribe to the channel. Leave a like and write a comment telling us where you are watching from and what time it is right now where you live. It is always strange to remember that people can be watching the same universe from different places on Earth, under different skies, at different hours of the night. Tonight, you are watching the Space for Sleep channel, talking about the universe is already dying, and it's terrifying. And to understand why that sentence is not just dramatic, we need to begin with something that sounds almost impossible. The universe is not dying because everything is suddenly ending. It is dying because the processes that made it bright are slowly running out. A living universe, in the cosmic sense, is not a universe filled with life everywhere. It is a universe where matter is still falling together, where gas clouds are still collapsing, where new stars are still forming, where galaxies are still changing, where heavy elements are still being created, and where energy is still concentrated enough to build structure. That is the universe we live in now. But it is not the universe at its peak. If you could see the cosmos the way an astronomer sees it, not just as a black sky with stars, but as a timeline stretching back 13.8 billion years, you would notice something unsettling. The universe was once far more active than it is today. Galaxies were forming stars faster. Clouds of gas were richer. Collisions were more common. Young stars were blazing into existence across huge regions of space. The cosmic night was not calm. It was busy, violent, crowded, and full of new light. Then, slowly, that activity began to fade. Not all at once, not in a single cosmic disaster, but quietly, across billions of years, the universe began to mature. And maturity, for the cosmos, means that the raw material for new stars becomes harder to find. That is the first clue. Stars do not appear from nowhere. They are born from gas, mostly hydrogen, collapsing under gravity. When enough material gathers in one place, pressure and temperature rise. Deep inside the growing object, atoms begin to fuse. Hydrogen becomes helium. Light escapes. A star is born. This process sounds endless until you remember that the supply is not infinite. In practice, gas can be used. Gas can be heated. Gas can be blown out of galaxies. Gas can be locked inside old stars, white dwarfs, neutron stars, planets, and black holes. And once a galaxy loses the cold gas it needs for star formation, it can remain filled with billions or trillions of stars, while slowly becoming a place where almost nothing new is being born. This is why some galaxies are called dead. They are not empty. They are not gone. They are not lifeless in the everyday sense. They are dead because they no longer form many new stars. A dead galaxy can still shine with the light of old stars. It can still be massive. It can still be beautiful through a telescope. But its youth is over. Its blue stars have burned out. Its star-forming clouds have disappeared or been heated beyond use. Its brightest nurseries have gone quiet. It becomes a cosmic city where the lights are still on, but no new buildings are rising. That image matters because the universe is slowly moving in that direction. Not every galaxy at the same speed, not every region equally, but on the largest scales, the trend is real. The universe once formed stars much more rapidly than it does now. Astronomers call this the cosmic star formation history. By looking at galaxies at different distances, they're also looking at galaxies at different times, because light takes time to travel. A galaxy 5 billion light-years away is not being seen as it is now. It is being seen as it was 5 billion years ago. A galaxy 10 billion light-years away is a message from a younger universe. When astronomers arrange those messages by time, a pattern appears. The universe's star-forming activity rose after the Big Bang, reached a great peak billions of years ago, and then began declining. We are living after that peak. That does not mean the universe is dark yet. It does not mean starbirth has stopped. In our own Milky Way, new stars still form inside giant molecular clouds. The Orion Nebula is a nearby example, a glowing region where young stars illuminate the gas around them. Across the cosmos, many galaxies are still active. Some are forming stars at incredible rates. Some are colliding and triggering fresh bursts of starbirth. Some contain black holes that reshape their surroundings with jets and radiation. But the overall age of easy star formation is passing. The cosmic furnace is still burning, but the fuel flow has slowed. This is one of the quiet reasons the title of tonight's journey is so disturbing. The universe does not need to explode to die. It only needs to run out of ways to renew itself. To understand how this happens, we need to think about galaxies not as fixed objects, but as living systems of gas, stars, dust, dark matter, and motion. A galaxy is not just a collection of stars. In fact, a young galaxy's future depends heavily on what exists between the stars. That space may look empty from far away, but inside galaxies, it contains gas clouds, dust grains, magnetic fields, cosmic rays, and regions where matter is constantly being stirred by gravity and radiation. Cold gas is especially important. Cold gas can collapse. Hot gas resists collapse. That single difference helps decide whether a galaxy becomes a place of birth or a place of fading memory. When a region of gas cools enough, gravity can begin gathering it into denser clumps. Those clumps fragment into smaller structures. Some of them become protostars. Around many of those protostars, disks form. Inside those disks, planets may eventually grow. In this way, a cold cloud becomes not only stars, but possible worlds. So when the universe loses cold gas, it is not only losing new stars, it is losing future solar systems. It is losing future planets. It is losing future chances. This is why the decline of star formation feels different from simply saying old stars will eventually burn out. It means the cosmic engine that makes new stages possible is weakening. A star is not just a light. A star is a factory. Inside stars, simple atoms are changed into heavier elements. In the simplest stellar cores, hydrogen is fused into helium. In more massive stars, helium can become carbon and oxygen. Later stages can create neon, magnesium, silicon, sulfur, and iron. In supernova explosions and neutron star collisions, even heavier elements can be produced and scattered into space. The calcium in bones, the oxygen in water, the iron in blood, the silicon in rock, and the carbon in living tissue all depend on stellar history. The universe had to make those ingredients. It had to form stars, let them live, let some of them die, and then recycle their remains into new generations. That recycling is one reason the universe became interesting. The earlier stars formed from mostly hydrogen and helium, with almost no heavy elements. Later, generations formed from enriched gas. Planets like Earth required that enrichment. Rocky surfaces, oceans, atmospheres, chemistry, and biology all depend on materials created in earlier stars. So a universe where star formation declines is not only becoming dimmer, it is becoming less productive. There may still be many habitable places. There may be planets forming long after Earth is gone. Red dwarf stars may support worlds for trillions of years. But the great era of building the raw ingredients in abundance is not something that lasts forever. In the beginning, the universe was too hot for stars. Then, it cooled enough for atoms. Then darkness came. Then gravity gathered matter. Then the first stars ignited. Then galaxies grew. Then stars enriched the cosmos. Then planets appeared. Then, in at least one place, life became aware of the sky. This is not a circle. It is an arrow. And arrows point somewhere. The terrifying part is that the arrow does not point toward more light forever. It points toward exhaustion. Let us slow down and look at the first great stage of this story. The early universe was not dying. It was being born into structure. After the Big Bang and the first moments of expansion, matter was spread through space, with tiny differences in density. These differences were small, but gravity had patience. Slightly denser regions pulled in more matter. More matter made them denser still. Over time, the cosmic web began to form. This web is one of the largest structures in the universe. Galaxies are not scattered randomly like dust thrown into a room. They gather along vast filaments of dark matter and gas. Between those filaments are enormous voids, regions so large that entire galaxies seem almost absent. Clusters form where filaments meet. Galaxies fall into those clusters. Matter flows along the web like rivers feeding distant cities. In the young universe, these rivers mattered. They delivered gas. They helped galaxies grow. They provided the material needed for star formation. A galaxy that can keep receiving fresh cold gas can keep forming stars for a long time. A galaxy cut off from that supply begins to use what it already has. Once that reservoir is gone, it becomes harder to restart. This is one way galaxies begin to die. Astronomers sometimes describe this as quenching. A quenched galaxy has had its star formation suppressed or stopped. The cause can vary. A galaxy may use up its gas in a powerful burst of star formation. A supermassive black hole at its center may pour energy into surrounding gas, heating it or pushing it away. A galaxy falling into a cluster may have its gas stripped by the hot plasma between galaxies. A collision may transform its structure. Over time, the bright blue glow of young stars fades, leaving older, redder populations behind. Blue stars are short-lived. Red stars live longer. This is important because color reveals age. A galaxy with many massive young stars can look blue because hot stars shine strongly in blue and ultraviolet light. But those stars burn their fuel quickly. Some last only millions of years. When star formation stops, the blue stars disappear first. The galaxy becomes redder as the longer-lived, cooler stars dominate. This is why a red, quiet galaxy can be a sign of cosmic aging. It is not red because it is angry or burning hotter. It is red because its brightest young stars are gone. In a photograph, such galaxies can look peaceful. Smooth elliptical galaxies, glowing softly with old starlight, may appear serene, but their calm is the calm after a fire has gone out. They are filled with stars, yet poor in the kind of cold gas that would make the next generation. The universe is full of these fossil cities, and more galaxies may join them with time. Our own Milky Way is not dead. It still forms stars, though not at the frantic pace of younger cosmic eras. It contains giant molecular clouds. It has stellar nurseries. It has young clusters But the Milky Way is also an aging system. The Sun itself is about 4.6 billion years old, and it formed long after the galaxy began building stars. In a sense, our star arrived late to the Milky Way's long star birth story. That fact is strangely personal. Earth exists because the universe was old enough to have made heavy elements before us. But we also exist after the most intense cosmic creation had already passed. We are children of a mature universe. Not the first darkness, not the first stars, not the first galaxies. We arrived after many generations of light had already lived and died. That timing is lucky for chemistry, but it also means we are looking at a cosmos whose future will not resemble its youth. If we could compress cosmic history into a human lifetime, the universe around us would not be a newborn. It would not even be in early childhood. The first wild burst of formation has passed. The galaxies have taken shape. Heavy elements have been distributed. Many stars that once burned fiercely are already gone. Black holes have grown. Clusters have assembled. Dark energy has begun shaping the large-scale future. The universe is still active, but it is no longer young. That is the first emotional shift we need to make. When people imagine the death of the universe, they often imagine something impossibly far away, a final darkness so remote that it belongs to philosophy more than science. But the process does not begin at the end. It begins with trends that can already be measured. Star formation is lower than it used to be. Many galaxies have already stopped forming stars. The expansion of space is carrying distant regions away from each other. The night sky of the far future will contain less reachable light. These are not predictions pulled from imagination. They are consequences of what astronomers already observe. To see the universe dying, you do not need to wait until the last star fades. You only need to notice that the rate of renewal is declining. Imagine a forest where old trees still stand everywhere. From a distance, the forest looks healthy. It is green. It is tall. It is full of shade. Birds still move through it. Wind still touches the leaves. But when you look closer, almost no young trees are growing beneath the canopy. The seeds are failing. The soil is drying. The old trees may last for a long time, but the forest's future has changed. The universe is not exactly a forest, but the comparison helps. Stars are still shining, galaxies are still bright, but the cosmic seedlings are becoming fewer. And once the process runs far enough, brightness can remain while renewal is already lost. That is why the death of the universe is not a single event. It is a long change in what the universe can still do. Now we need to ask what caused the universe to be so alive in the first place. Why did star formation rise after the Big Bang? Why did it peak? Why did it decline? The answer begins with density. The early universe was denser than it is now. Matter was closer together. Gas could fall into growing structures more easily. Galaxies collided more often because the universe was smaller and more crowded compared with today. Those collisions could compress gas and trigger enormous waves of star formation. Fresh material was still flowing into young galaxies. The cosmic web was actively feeding them. The early universe was also less settled. Galaxies were smaller, messier, and more turbulent. They had not yet aged into the grand spirals and smooth ellipticals we see today. Many were irregular, many were merging. Many were packed with gas. Their stars formed under conditions that could be chaotic and intense. This was not a calm universe. It was a construction site. If you could somehow float safely outside a young galaxy during one of its active phases, you might see vast regions glowing with newborn stars. Huge clouds would shine in pink and blue light as ultraviolet radiation ionized the surrounding gas. Massive stars would carve bubbles in their birth clouds. Supernovae would erupt. Shock waves would compress nearby material. Black holes might flare as gas poured into them. Creation and destruction were not opposites there. They were partners. A massive star could live fast, explode, and scatter heavy elements into space. That explosion could also push gas into new shapes, sometimes triggering more star formation elsewhere. The death of one generation could help prepare the next. The universe's early brightness came from this restless cycle. But cycles depend on supply. Over time, gas is consumed. Some of it becomes long-lived stars. Some is locked into remnants. Some is ejected into intergalactic space. Some becomes too hot to collapse easily. Some is disturbed by black holes or stripped from galaxies in clusters. The clean, cold material needed for efficient star formation becomes harder to gather. Galaxies also grow larger and more stable. Stability can be beautiful, but it can reduce the turbulence that once fueled rapid change. A settled spiral galaxy may still form stars along its arms, but not necessarily at the furious rate of a young merging galaxy. A giant elliptical may contain enormous mass while producing little new light. The universe's youth was noisy because matter had not yet found its long-term arrangements. The universe's old age will be quiet because much of matter will be locked into things that no longer easily transform. This is a key idea. Death in the cosmos often means the loss of transformation. A white dwarf is not gone, but it no longer fuses atoms in its core. A neutron star is not gone, but it is no longer a normal star. A dead galaxy is not gone, but it no longer builds many stars. A cold universe may still contain matter, but less and less of that matter will be arranged in ways that create new sources of light. The future is not empty at first. It is full of leftovers. This is what makes it so eerie. The universe will not die by disappearing immediately. It will die by becoming a museum of its own past. Old stars, stellar remnants, black holes, cold planets, faint radiation, ancient particles, structures drifting apart, evidence of former brilliance, but fewer engines still making more. Before we go too far into the future, we need to understand the role of the stars that still dominate the present. Stars are not all the same. Their mass determines much of their fate. Massive stars burn hot and die young. Medium stars, like the Sun, live for billions of years before swelling into red giants and ending as white dwarfs. Low-mass red dwarfs burn slowly, quietly, and with extraordinary patience. Some of them may last trillions of years. This means the universe's light does not fade evenly. The most dramatic stars disappear early. The quietest stars remain. In a young star-forming galaxy, the brightest massive stars can dominate the view. They are luminous, blue, and powerful. But they are also brief. Their lives may last only a few million years, which is less than a cosmic blink. They explode as supernovae or collapse into black holes, leaving behind enriched gas and energetic remnants. These stars are like fireworks. Red dwarfs are like embers. They are small, dim, and long-lived. Because they consume their fuel slowly, they can survive far longer than stars like the Sun. In the far future, after Sun-like stars are gone and massive stars are long extinct, red dwarfs may provide the last ordinary starlight in the universe. That future is not empty, but it is dim. A cosmos dominated by red dwarfs would not look like the sky we know. The brightest, shortest-lived stars would be gone. Star-forming regions would be rare. Large blue stars would no longer mark young stellar nurseries. The universe would glow faintly in red and infrared, with long-lived stars continuing quietly after the grand age of starbirth has ended. This is part of the terror. The future of the universe is not only darkness, it is the slow removal of spectacle. The great brilliant stages happen earlier. The long remainder is quieter. Human beings are drawn to dramatic endings, but the cosmos often prefers slow ones. A star can take billions of years to die. A white dwarf can cool for longer than the universe has existed so far. A black hole can evaporate over timescales so immense that ordinary language fails. The end is not a closing door. It is a corridor that keeps stretching. And we are near the beginning of that corridor. That may sound comforting, but it also changes how we see the present. We are not living at the end of all light. We are living during a temporary interval when enough stars still shine, enough elements exist, enough planets have formed, and enough cosmic history remains visible for conscious beings to study it. This age will not last forever. One day, far in the future, astronomers in a galaxy like ours may not see the same universe we see. If dark energy continues to drive the accelerated expansion of space, distant galaxies beyond the local group will eventually move so far away that their light can no longer reach future observers. The cosmic microwave background will be stretched to extremely long wavelengths. Evidence of the Big Bang may become harder, perhaps nearly impossible, to detect from inside a gravitationally bound island of stars. Future minds could live in a universe that appears smaller and lonelier than ours. They might see their local galaxy group and little else. They might not know, from direct observation, that the universe once contained billions of visible galaxies spread across an expanding cosmic web. In that sense, the universe is not only losing star formation, it may also be losing memory. Not because records vanish by magic, but because the light that carries information is being stretched away. This is one of the most unsettling ideas in cosmology. The universe can hide its own past from its future inhabitants. We live at a time when the cosmic background is still observable, when distant galaxies are still visible, when the large-scale structure of the universe can still be mapped, and when star formation has declined but not vanished. Our era may be unusually rich in evidence. We can see the afterglow of the early universe. We can observe galaxies across deep time. We can compare young and old cosmic regions. We can reconstruct a story from the clues that still reach us. A much later universe may not offer the same clues. If intelligence arises in the far future, it may look outward and see a dark sky with fewer answers. The universe dying, then, is not only a physical process, it is also an informational one. Less light, fewer new stars, fewer visible galaxies, fewer accessible traces of origin. This does not mean knowledge disappears everywhere at once. Civilizations could preserve information, physics would still operate. Local stars could still be studied. But the universe itself would become less generous with evidence. The cosmic library is slowly closing its outer rooms. That phrase sounds poetic, but the mechanism is physical. Space expands, light redshifts, distant galaxies cross horizons, gas supplies decline, stars exhaust fuel, remnants cool, entropy increases. Step by step, the universe moves from hot differences toward cold sameness. Entropy is a word that often gets used vaguely, but for this story, it matters deeply. One way to think about entropy is as the spreading out of usable energy. A hot star beside cold space represents a difference. Energy can flow. Work can happen. Planets can be warmed. Atmospheres can move. Chemistry can be powered. But when energy becomes evenly spread, when there are fewer differences to exploit, the universe becomes less capable of doing interesting things. Life depends on differences. A planet receives energy from a star and radiates energy back into space. That flow powers weather, oceans, photosynthesis, and climate systems. A living cell depends on chemical gradients. A civilization depends on concentrated energy sources. Even a star exists because gravity concentrates matter and fusion releases energy. The universe becomes less alive when those differences fade. This is the deepest meaning of cosmic death, not the destruction of every particle, not a sudden moment when existence stops, but a future where energy is so spread out and matter so locked away that the universe can no longer build, burn, shine, or remember in the ways it once did. This is why the phrase "already dying" is scientifically meaningful. Entropy has been increasing since the beginning. Stars are using fuel right now. Galaxies are exhausting gas right now. Black holes are growing right now. Expansion is separating structures right now. The future is not an unrelated catastrophe waiting somewhere beyond imagination. It is the continuation of trends already underway. But the story is not only dark. To understand why, we need to look more carefully at what death produces before it completes its work. When stars die, they do not simply remove light, they create complexity. Massive stars enrich galaxies. Supernovae scatter elements. Neutron star mergers can produce heavy metals. Red giants release carbon-rich material into space. Planetary nebulae expose glowing shells of gas. White dwarfs preserve the cores of old stars. A dying universe is also a universe that has produced everything it needed to become complex. The same aging process that leads toward darkness also allowed planets like Earth to exist. If the universe were too young, there would not be enough heavy elements. If it were too old, many sources of renewal would be gone. We exist in the middle, after creation became rich, but before it becomes too scarce. That timing is one of the quiet miracles of cosmology. The universe had to age in order to make us, but if it ages long enough, it becomes less capable of making worlds like ours. This is why the present is so precious. Not because it is the center of time, not because the universe was made for us, but because our era is one of the rare intervals when the cosmic story is both mature and still luminous. There is enough past to make heavy elements. There is enough present light to support life. There is enough visible distance to understand the larger story. That combination will not last forever. Now let us return to the stars, because they are the clocks that make cosmic death visible. The sun is middle-aged. It has been shining for about 4.6 billion years and has roughly 5 billion years left before it becomes a red giant. For human civilization, that future is so far away that it feels abstract. But for the universe, the sun is temporary. Every sunrise is powered by a process that consumes fuel. The sun shines because hydrogen is being turned into helium in its core. The light that warms Earth is part of a slow conversion of mass into energy. The sun is stable because gravity and pressure are balanced. Gravity pulls inward. Fusion-generated pressure pushes outward. As long as the core can fuse hydrogen steadily, the star remains in its main sequence life. But the hydrogen in the core is finite. Eventually, the balance changes. The core evolves. The outer layers expand. The sun becomes a red giant. Earth's future becomes unrecognizable. Our star is not unusual in this. Most stars are temporary arrangements. They are born because gravity wins locally. They live because fusion resists gravity. They die when the fuel structure changes. A galaxy is therefore a field of clocks, each one ticking at a different pace. Massive stars run fast. Small stars run slow. Some clocks end in explosions, others fade. Some leave dense remnants, some become black holes. Together, they mark the universe's transformation, from a bright, creative age to an old remnant age. When we look at a galaxy, we are seeing clocks at different stages. Blue regions mark youth. Yellow stars mark maturity. Red stars mark long endurance. White dwarfs mark spent cores. Nebulae mark transitions. Supernova remnants mark violent endings. Black holes mark collapsed gravity. The universe is not a still picture. It is a clockwork of endings. And every ending shifts the balance of the future. If new stars keep forming, death becomes part of renewal. If new stars stop forming, death becomes accumulation. That distinction is crucial. In a young, active galaxy, old stars die while new stars are born. The population changes, but the galaxy remains alive. In a quenched galaxy, old stars still die, but fewer new ones replace them. Over time, the stellar population ages. Massive stars vanish. Medium stars evolve. Low-mass stars remain. The galaxy grows dimmer and redder. Now, expand that idea from one galaxy to the universe. As cosmic star formation declines, the universe as a whole shifts from replacement toward accumulation. More remnants, fewer newborn stars, more old light, less fresh fuel. The present cosmos is not dead, but it is carrying the signs of aging. One reason this can be hard to feel is that human time is tiny. 1,000 years is huge for history. 1,000,000 years is huge for species. 1,000,000,000 years is huge even for planets. But for the final fate of stars, galaxies, and black holes, 1,000,000,000 years can be a chapter, not the book. This difference in scale makes cosmic death seem unreal. Nothing in the sky appears to change much in a human lifetime. The constellations remain familiar. The sun rises, the moon orbits. The Milky Way still arches across dark skies where light pollution allows it. Galaxies photographed by telescopes look frozen in place. But stillness is an illusion created by short lives. The universe is changing constantly, just too slowly for our bodies to notice. The Andromeda Galaxy is moving toward the Milky Way. In several billion years, the two will merge. The sun is slowly growing brighter. Stars are being born and dying across the galaxy. Black holes are swallowing matter. White dwarfs are cooling. The cosmic background is redshifting. Distant galaxies are becoming less accessible. The death of the universe is already written in motions that are happening now. We simply do not live long enough to watch the sentence finish. That is why astronomy is a time machine. It lets us observe different stages at once. Nearby objects show us the present neighborhood. Faraway galaxies show us the younger universe. Stellar remnants show us possible futures. Red dwarfs show us long endurance. Dead galaxies show us what star systems can become when birth slows. The cosmic microwave background shows us the ancient afterglow of a hot beginning. By assembling these pieces, we do not have to wait for the future to know what direction the universe is moving. We can read the pattern. And the pattern says, the bright age is temporary. Let us talk about dead galaxies more deeply, because they are like previews of the larger cosmic fate. A galaxy can die in several ways. One path is starvation. A galaxy stops receiving enough fresh gas from the cosmic web. It slowly uses the gas it has, and star formation fades over time. This is not dramatic from the outside. There may be no single explosion or collision. The galaxy simply loses the ability to keep replenishing itself. Another path is feedback. A supermassive black hole at the center of a galaxy can become active when gas falls toward it. The region around the black hole can release extraordinary energy. Jets can blast outward. Radiation can heat surrounding material. Winds can push gas out of the galaxy or prevent it from cooling. In this way, the central black hole can help shut down star formation across a much larger system. A third path is environmental stripping. When a galaxy falls into a cluster, it moves through hot gas that fills the space between galaxies. This can strip away its own gas, like wind tearing leaves from a tree. The stars remain, but the material needed to form new stars is removed. A fourth path is rapid consumption. A collision or merger can trigger an intense starburst, converting huge amounts of gas into stars quickly. After the burst, little usable gas remains, and the galaxy settles into quiet aging. These paths are different, but they lead toward a similar result. A galaxy full of old stars. A galaxy with little birth. A galaxy shining with memory instead of promise. The terrifying part is not that these galaxies exist. The terrifying part is that they may represent the direction of cosmic history. Not every galaxy is dead today. The universe still contains spirals, starbursts, irregular galaxies, and gas-rich systems. But as time passes, more gas becomes unavailable. More stars age. More galaxies merge into larger systems. More material falls into black holes or remnants. The large-scale trend favors quiet. We live in an era where both states are visible. We can see galaxies that are young and active. We can see galaxies that are old and quiet. That means we are witnessing the transition, not just imagining it. This transition also changes the kinds of planets the universe can build. Early in cosmic history, there were fewer heavy elements. Rocky planets may have been less common. Later, after generations of stars enriched the gas, planet formation became more chemically rich. Today, the universe contains countless planets, including rocky worlds, gas giants, ice giants, super-Earths, mini-Neptunes, and rogue planets drifting between stars. But if star formation continues to decline, the formation of new planetary systems also declines. Again, this does not mean existing planets vanish. They can persist for immense times, but the rate at which new potential homes appear will slow. This matters for life. Life, as far as we know, needs environments where chemistry can remain active for long periods. Stable stars, suitable planets, liquid solvents, energy flows, protective atmospheres, and enough heavy elements all matter. The universe spent billions of years creating these conditions. It may continue to create them for a very long time, especially around long-lived stars. But eventually, the cosmic factory becomes less productive. The death of the universe is therefore not only about the last star. It is about the fading probability of new beginnings. A universe can be full of objects and still become less fertile. That word, fertile, may be the best way to understand the early and middle cosmos. The young universe became fertile after stars enriched it. The mature universe remains fertile where gas still gathers and stars still form. The far future becomes increasingly sterile as fuel is locked away and differences fade. Fertility does not last forever in a closed physical process. Even if the universe is infinite in size, any given region can exhaust its usable resources. And because expansion carries regions apart, what happens in one region may become forever disconnected from another. This brings us to dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. Scientists do not yet know its true nature. It may be a property of space itself. It may behave like a cosmological constant. It may be something more complicated. But observations show that distant galaxies are not merely moving apart. On the largest scales, the expansion is speeding up. This has an enormous consequence for the universe's death. Gravity can hold local structures together. The Milky Way and Andromeda are bound. Galaxy clusters can remain bound. Solar systems remain bound. Planets remain bound to stars unless other events disturb them. Dark energy does not tear apart small structures under the standard picture. But on vast scales, it drives distant galaxy groups away from each other, faster and faster. This means the universe's future is not just older, it is more isolated. Imagine islands on an ocean, where the water between them keeps stretching. The islands themselves remain intact. People on one island can still walk around, build, remember, and watch their local sky. But the other islands recede. Their lights grow dimmer. Messages take longer. Eventually, no new message can cross the expanding gap. That is what accelerated expansion does to cosmic neighborhoods. The local group may remain together, eventually forming a larger merged galaxy, sometimes called Milkomeda, after the Milky Way and Andromeda merge. But galaxies far beyond our gravitationally bound region will drift out of reach. Their light will be redshifted and dimmed. The observable universe of future observers will shrink in practical terms, even if space itself continues. The sky will lose context. This is one of the loneliest parts of cosmic death. The universe does not need to remove every star around you to make you isolated. It only needs to carry the larger universe beyond your horizon. The present sky still gives us a grand view. We can see galaxies billions of light years away. We can detect the cosmic microwave background. We can map large-scale structure. We can infer expansion. But in the far future, a civilization inside the merged local group may see far fewer external galaxies. They may not easily detect the evidence that once told us the universe began hot and dense. The universe will become locally lit, but cosmically silent. That future is not the heat death yet. Stars may still shine. Planets may still orbit. Life may still exist somewhere. But the broader cosmic story will be harder to access. This is why the universe can be dying in stages. First, star formation declines. Then, galaxies age. Then, distant galaxies become unreachable. Then, the remaining stars burn out. Then, remnants cool. Then, black holes dominate. Then, even black holes fade through processes so slow they almost defy thought. Tonight's first half is about the early stages of that death, the ones already visible in the universe around us. The later stages belong to the second half, where the future becomes stranger, darker, and much longer than the entire age of stars so far. But before we reach that future, we need to understand one more thing about the present. The universe is not dying evenly. Different places are at different stages. Some galaxies are still blue and active, some are red and quiet, some are undergoing mergers, some are isolated, some are rich in gas. Some have been stripped. Some host powerful central black holes. Some are small dwarf galaxies where star formation flickers in bursts. Some are enormous ellipticals that look almost finished. This unevenness is why the universe remains interesting. If everything aged at the same rate, the sky would be simpler. Instead, cosmic history is layered. Young stars can exist inside an old galaxy. Dead galaxies can appear surprisingly early. Ancient stars can still orbit near regions of new star birth. A black hole can shut down one galaxy, while another nearby continues building stars. The universe is not a clock with one hand. It is a vast landscape of clocks, all ticking differently. That variety helps prevent the script of cosmic death from becoming a single repeated line. There are many ways to fade. There are many ways to survive. There are many temporary exceptions, but the largest trend remains. The universe is aging away from its brightest creative phase, and the evidence is written across the sky. Consider the Milky Way. Our galaxy contains hundreds of billions of stars, vast amounts of dark matter, gas clouds, dust lanes, stellar streams, globular clusters, and a central supermassive black hole called Sagittarius A. It is not a dead galaxy. It still forms stars. It still has spiral arms. It still contains rich structures where gas collapses into new systems. Yet the Milky Way also carries memories of earlier violence. It has absorbed smaller galaxies. It contains stellar streams, the stretched remains of systems torn apart by gravity. Its halo contains old stars. Its disk has grown over time. It is moving toward a future merger with Andromeda. The galaxy we know is only one stage. When the Milky Way and Andromeda eventually merge, the night sky of any surviving world would change dramatically. Stars themselves are so far apart that direct collisions between individual stars would be rare. but the galaxy's shapes would be transformed. Gas clouds could be compressed. Some star formation might be triggered. Over time, the two spirals would settle into a larger, more elliptical structure. This sounds like renewal, and in a limited sense, it is. Galaxy mergers can ignite star formation if enough gas remains. But mergers also help move galaxies toward later stages. They can feed central black holes. They can heat gas. They can transform organized disks into smoother systems. After the burst, the galaxy may become quieter than before. A collision can be both a last celebration and a step toward silence. This dual nature appears throughout cosmic history. Supernova destroy stars, but enrich space. Black holes consume matter, but shape galaxies. Mergers trigger starbirth, but can help quench future formation. Red giants end stable planetary eras, but return material to space. The universe dies by processes that also create beauty along the way. That is why the subject is not simply depressing. It is complex. The path toward darkness is lined with nebulae, new elements, altered galaxies, glowing remnants, and long-lived stars. Cosmic death is not ugly. It is magnificent, which almost makes it more frightening. A disaster that looked only like disaster would be easier to reject. The universe's decline is woven into the same physics that made everything possible. Gravity builds stars and eventually collapses cores. Fusion powers life and consumes fuel. Expansion gives space its history and isolates the future. Entropy allows time to have direction and leads toward exhaustion. There is no villain in this story. There is only physics continuing. That may be the most unsettling part. The universe is not dying because something went wrong. It is dying because the same rules that created light also limit how long light can last. Now let us focus on the phrase "already dying" from another angle. When did the death of the universe begin? You could say it began at the Big Bang, because entropy began increasing and the universe started moving through irreversible stages. You could say it began when the first stars ignited, because from the moment fusion started, fuel was being consumed. You could say it began when star formation peaked and then declined, because that marks the shift from rising activity to fading production. You could say it began when dark energy became dominant enough to accelerate expansion, because that sealed the isolation of distant cosmic regions. Each answer reveals a different layer. There is no single birthday for cosmic death. There are milestones. The beginning of time, the first stars, the peak of star formation, the rise of dead galaxies, the acceleration of expansion, the final era of starbirth, still far ahead, the last red dwarfs, the age of remnants, the age of black holes, the final fading. Tonight's first half is concerned with the milestones we can already see or infer from the present. We are not waiting for the first clue. We are surrounded by clues. The fact that star formation was once stronger, the fact that dead galaxies exist, the fact that the Milky Way's own star formation is modest compared with earlier cosmic epochs, the fact that the cosmic background is cooling, the fact that expansion is accelerating, the fact that every star has a lifetime. Each clue is small by itself. Together they form a direction. The universe is not static. It is not endlessly renewed at the same rate. It is not simply a stage on which eternal stars shine. It is a process, and processes can run down. Think of a candle. While it burns, it does not look like it is dying in a dramatic way. It gives light. It gives warmth. The flame dances. It may seem alive, but every second of brightness consumes wax. The candle's beauty and its disappearance are the same event from different perspectives. Stars are not candles in a simple chemical sense, but the image helps. A star's light is proof of its fuel consumption. A galaxy's glow is proof of its stellar population aging. A star-forming region's beauty is proof of gas being converted into something less available for the future. The universe shines by spending itself. This does not make the present less meaningful. If anything, it makes it more intense. Every photograph from a telescope is a picture of energy in transition. Every nebula is a temporary phase. Every galaxy is a changing system. Every planet is part of a clockwork that will not remain as it is. Even the cosmic microwave background, the oldest light we can observe, is cooling as space expands. Nothing we see is permanent. The universe is not a sculpture. It is a flame, and flames end. Now, there is a danger in exaggerating this. The universe is not about to go dark tomorrow. Stars will continue forming for a very long time. Red dwarfs will last beyond any ordinary imagination. The future contains more time than the past, by a staggering margin. If the universe is dying, it is dying on a scale that makes human history almost invisible. But long time scales do not cancel the direction. A mountain can erode slowly and still be eroding. A star can shine for billions of years and still be consuming its core. A civilization can live under a bright sky and still inhabit a universe past its creative peak. Cosmic death is slow enough to be mistaken for permanence. That is why it is terrifying in a calm way. Not because it rushes toward us, because it does not need to rush. The universe has more patience than fear. Let us move deeper into the decline of star formation. What exactly happens when a galaxy runs low on cold gas? The first change is not always visible to the naked eye. The galaxy may still shine brightly because its existing stars continue to glow, but the regions associated with young stars begin to weaken. Emission nebulae fade. Ultraviolet light decreases. The galaxy's color shifts. Spiral arms may become less defined if they are no longer marked by blue star-forming regions. Dust lanes may remain, but they no longer carry the same promise. Over time, massive stars die out. Since no new massive stars are replacing them, the galaxy loses its brightest short-lived lights. Supernova rates can decline. The remaining population is dominated by lower-mass stars, red giants, and stellar remnants. The galaxy's appearance becomes smoother and older. Inside that galaxy, planets may continue orbiting. Civilizations, if any exist, might not notice immediate danger. But the long-term environment changes. Fewer new stars mean fewer new planetary systems. Fewer supernovae mean less fresh enrichment, though also fewer nearby catastrophic explosions. Fewer molecular clouds mean fewer nurseries. The galaxy becomes safer in some ways and less creative in others. That tension is fascinating. A very active star-forming galaxy can be dangerous. Massive stars explode. Radiation is intense. Gravitational disturbances are common. A quieter galaxy may offer stable environments around long-lived stars. Life might prefer calmer places. But if calm becomes too complete, the galaxy stops making new homes. There may be a window where stability and renewal overlap. Perhaps we live in such a window. The Milky Way is not too young and violent. It is not fully dead. It is chemically mature. New stars are still being made inside it. It has stable regions where planetary systems can last. Earth's existence may depend on this balance. Too early, not enough heavy elements. Too late, less star formation and fewer visible clues. Now, this does not prove that our time is special in a mystical sense, but it does show that habitability is tied to cosmic timing. Life is not just about distance from a star. It is about when, in the universe's history, a planet forms, what materials are available, what kind of star it orbits, how violent the galaxy is, and how long stable conditions persist. A dying universe may still contain life for an enormous time, but the conditions for creating new life-bearing worlds may change. This is why cosmic death is not only about astronomy. It touches the question of whether life itself has an era. Could life be more common now than in the early universe? Could it remain common around red dwarfs far into the future? Could the peak age for life be ahead, even while the peak age of star formation is behind? Scientists do not know. The answer depends on many uncertainties. How often life begins, how long planets remain habitable, whether red dwarf planets can keep atmospheres, how common stable oceans are, and whether biology can survive around active small stars. So the story has room for hope. The universe may be dying in a thermodynamic sense, while life still has vast future possibilities. That is not a contradiction. A dying forest can still contain living creatures. An aging galaxy can still host inhabited worlds. A declining universe can still produce rare and meaningful islands of complexity. But those islands exist against a background trend, and the trend remains toward less renewal, less connection, and less usable energy. The first half of our journey has brought us to that understanding. The universe is already dying because the creative mechanisms that once made it blaze are weakening. Star formation peaked long ago. Cold gas is becoming harder to gather. Galaxies can stop giving birth to stars. Black holes can heat and expel the material galaxies need. Expansion can isolate cosmic regions. Every star shines by spending fuel it cannot keep forever. And yet, the sky above us is still full of light. This is the strange middle place we occupy. We are not at the beginning. We are not at the end. We are in the afterglow of cosmic youth, surrounded by enough brightness to forget that brightness is temporary. The next part of the story takes us farther forward. Not just millions of years. Not just billions, but trillions, quadrillions, and beyond. We will follow the last ordinary stars, the cooling white dwarfs, the frozen planets, the long rule of black holes, and the final question of whether the universe ends in silence, darkness, or something stranger. Because if the universe is already dying, then the most terrifying question is not whether the process has started. It is what remains after the lights finally stop coming back. That question takes us beyond the ordinary age of galaxies, into a future where the universe does not suddenly end, but gradually loses the ability to renew itself. At first, the change would not look dramatic. If you could somehow survive far into the future and stand on a world still orbiting a quiet star, the sky might not appear broken. There would still be points of light overhead. There would still be galaxies beyond your own, at least for a while. There would still be nebulae, star clusters, dead stars, planets, dust, and the slow motion of gravity shaping matter into familiar forms. But the important difference would be hidden inside the numbers. Fewer bright blue stars would appear. Fewer newborn clusters would ignite inside clouds of hydrogen. Fewer galaxies would glow with the fresh ultraviolet light of young stellar nurseries. The universe would not be empty yet. It would not be silent in the absolute sense. It would still contain heat, radiation, motion, gravity, and structure. But it would be living mostly on what it had already made. That is one of the strangest ways to understand cosmic death. A living universe, in the broadest physical sense, is not simply a universe that contains objects. It is a universe with gradients, hot places and cold places, dense clouds and open voids, fresh fuel and burned ash, regions where energy can still flow from one state into another, places where gravity can still compress gas until stars are born, places where nuclear fusion can still turn simple elements into light. A dying universe is not one where everything vanishes at once. It is one where fewer transformations remain possible. To see why, imagine the future of the Milky Way long after our time. The galaxy is still there. It still contains hundreds of billions of stars, or the remnants of stars. It still turns slowly under its own gravity. It still carries dark matter in a vast, invisible halo. But the glowing spiral arms that once marked waves of starbirth are dimmer. The clouds that once collapsed into clusters have been scattered, heated, consumed, or locked away. Stars do not appear from nothing. They require cold gas. They require enough density. They require turbulence, compression, gravity, and time. When a galaxy is young, it can be rich in gas. The early universe gave galaxies enormous reservoirs of hydrogen and helium. Collisions between galaxies stirred that material. Shockwaves squeezed it. Supernovae both disturbed and enriched it. The whole system was messy, violent, and productive. But every generation of stars changes the supply. Some gas falls into stars and remains trapped for millions, billions, or trillions of years. Some becomes heavy elements. Some is blasted outward by stellar winds and supernovae. Some is heated until it becomes too energetic to collapse easily. Some is thrown into the halo around a galaxy. Some is lost into intergalactic space. A galaxy can recycle material, but recycling is not perfect. Each cycle leaves less cold, clean fuel available for the next one. This is why the future universe becomes redder. Massive blue stars burn fast. They are spectacular, but brief. They live for only a few million years, sometimes less than the time it takes a single spiral arm to rotate by a small angle. They flood space with ultraviolet light, then explode or collapse. When star formation slows, blue stars disappear first, because they were never built to last. Yellow stars, like the sun, remain longer. Orange stars remain longer still. Red dwarfs become the true survivors. And that changes the color of existence. A universe filled with young stars can look brilliant, restless, and sharp. A universe dominated by old stars looks softer, dimmer, and colder. Not because every star is gone, but because the short-lived lights have already spent themselves. This is where the death of the universe becomes less like an explosion and more like a room where lamps are being turned off in order of brightness. The first lamps to go are the most powerful. The last are the smallest, faintest, and most patient. Red dwarf stars are especially important because they can live for astonishing lengths of time. A small red dwarf uses its hydrogen slowly and efficiently. Unlike the Sun, which mostly fuses hydrogen in its core and leaves outer layers less involved, many red dwarfs can mix their interiors more thoroughly. Fuel that might otherwise remain unused can be brought into the fusion region. Their low mass means lower pressure, lower temperature, and a much slower rate of nuclear burning. The result is a kind of stellar endurance that almost feels unreal. The smallest red dwarfs may shine for trillions of years. Some estimates stretch their possible lifetimes into the tens of trillions. The current universe is only 13.8 billion years old, so no red dwarf has had enough time to finish its full life cycle. Every red dwarf ever born, unless destroyed by collision or stripped by some unusual event, is likely still shining today. That means the future universe will not become dark immediately after stars like the Sun disappear. It will enter the long age of red light. Imagine galaxies where the great blue stars are gone, where sun-like stars have aged into white dwarfs, where giant nebulae no longer glow with the same strength, but countless small red stars continue burning quietly. Their light is weak. Their habitable zones are close in. Their planets, if they have them, may orbit under skies dominated by a dim, crimson star. Around some of these stars, planets could remain warm for periods far longer than Earth will ever enjoy around the Sun. This part of the future is not pure extinction. It may even be the longest age in which life could exist. That is one reason the idea of a dying universe is so disturbing. It does not simply erase possibility. It stretches it into shapes that are hard for us to recognize. Life, if it exists around red dwarfs in the far future, may look up at a sky with fewer visible galaxies, fewer bright stars, and less evidence of the earlier universe. It may inherit a cosmos already past its creative peak. Those future beings, if they ever exist, might not know the universe had a bright youth. They might not see the cosmic microwave background clearly. They might not see distant galaxies in every direction. They might live in a universe where expansion has carried most other galactic systems beyond their observable horizon. Their science could be built inside a much smaller apparent cosmos. That does not mean they would be unintelligent. It means the universe would give them fewer clues. And that is another kind of cosmic death. Not the death of matter. Not the death of every star. The death of evidence. As dark energy continues to accelerate cosmic expansion, distant galaxies move away from us faster and faster. Locally bound systems, like the Milky Way and Andromeda and the other members of our future merged galaxy, remain held together by gravity. But galaxies outside our gravitational neighborhood drift toward permanent separation. Their light becomes stretched. Their images grow dimmer. Their signals arrive more slowly. Eventually, after enough cosmic time, many of them will no longer be observable. They will still exist, somewhere beyond our reach, at least for a while. But from the point of view of observers in our far future, they may as well have vanished. The universe will not have become smaller. The visible part will have. This creates a strange reversal. Early observers like us can look outward and see a universe filled with evidence of its own history. We can detect the cosmic microwave background. We can see galaxies at many ages. We can study stellar populations, supernovae, quasars, gravitational lensing, dark matter, and the large-scale web. We live at a moment when the universe is old enough to have formed complexity, but young enough that its past has not been hidden from us. That window will not stay open forever. A civilization born trillions of years from now might look out and see mostly its own island of stars. It might conclude that the universe is static, local, and much smaller than it really is. It might never discover cosmic expansion in the way we did. It might not know that galaxies once filled the observable sky. This is not because its telescopes would be weak. It is because the signals would be gone. In that sense, the universe is already carrying away its own autobiography. Every moment, photons from distant structures cross space toward us. Some arrive. Some will arrive in the future. Others will never arrive, because the expansion of space prevents them from closing the distance. The story of the universe is not stored in one place. It travels as light, and light can be delayed, stretched, diluted, and eventually lost beyond horizons. The death of the universe is therefore not only about stars running out of fuel, it is also about information becoming unreachable. And yet, before that long isolation becomes complete, the stars themselves must pass through their own endings. Sun-like stars will leave behind white dwarfs. A white dwarf is not a star in the ordinary sense. It no longer fuses hydrogen in a stable core. It is the exposed remnant of a star that has shed its outer layers. It is incredibly dense, Earth-sized, but containing a large fraction of a star's mass. It glows because it is still hot from its past, not because it is generating new energy in the way the sun does. White dwarfs are embers. At first, they can shine fiercely, hot and blue-white. Over time, they radiate their stored heat into space. With no major internal furnace to restore that heat, they cool. The process is slow because a white dwarf is compact and dense. It can remain visible for billions upon billions of years, but given enough time, even white dwarfs fade. The universe is not old enough for any true black dwarf to exist yet. A black dwarf would be a white dwarf that has cooled so much that it no longer emits significant visible light. It would be a cold, stellar corpse, still massive, still gravitationally present, but dark. In the remote future, galaxies may be filled with these objects: white dwarfs cooling toward black dwarfs, neutron stars losing heat, old planets frozen around dim remnants, brown dwarfs never massive enough to ignite hydrogen fusion in the first place, black holes waiting in the centers of galaxies and scattered through the remains of ancient stellar populations. This future has structure, but very little glow. The first half of cosmic death is the exhaustion of ordinary star formation. The second half is the fading of everything that was already made. There are still events during this age, but they become rare. Stars pass near one another only occasionally. Dead remnants can collide, binary white dwarfs can spiral together and explode. Neutron stars can merge, black holes can swallow companions. A quiet galaxy can briefly flare when an object passes too close to its central black hole. But the rhythm changes. The universe no longer resembles a forest growing new trees every season. It becomes more like an old landscape where ancient trunks collapse one by one, with long silences between them. Gravity does not stop working. That is important. Even in a dying universe, gravity keeps rearranging what remains. Star systems can be disrupted by passing stars. Planets can be thrown into interstellar space. Stellar remnants can sink toward galactic centers over enormous timescales. Some objects are ejected from galaxies entirely. Others fall inward. A galaxy in the far future may slowly evaporate in a gravitational sense, not by turning into gas, but by scattering its members through repeated interactions. When stars and remnants pass near each other, they exchange energy. Some lose energy and move inward. Others gain enough energy to escape. Over vast periods, a galaxy can lose many of its objects into the dark between galaxies. That dark between galaxies will itself become colder and emptier. A rogue planet drifting there would receive almost no starlight. If it had internal heat, it might keep a subsurface ocean for a while, depending on its mass and composition. If it did not, it would freeze deeper and deeper. Its atmosphere might collapse onto the surface. Its chemistry would slow. Its sky would contain fewer visible points as cosmic expansion and stellar death removed sources of light. This is one of the loneliest images in the future universe. A planet without a star, moving through a region where the galaxies are too far away to matter, carrying only the heat left inside itself. Such worlds may already exist today, but in the far future they become more common in spirit. More planets become unmoored. More systems lose their warmth. More objects become dark travelers, no longer connected to the bright engines that once made them visible. Eventually, the red dwarfs also end. This is difficult to imagine because their lifetimes are so long compared to the age of the universe. But they are not eternal. Hydrogen fusion, no matter how efficient, consumes fuel. A red dwarf may avoid becoming a red giant like the Sun. Depending on its mass, it may slowly transform as helium builds up and hydrogen becomes depleted. It may become hotter and bluer for a time, then contract toward a white dwarf-like remnant. The details depend on mass, but the destination is the same in the broad sense. The last true stars will stop being stars. When that happens, the stelliferous era, the age of stars, ends. This is one of the great thresholds in cosmic history. The universe began with no stars. Then it entered an age filled with them. After an unimaginably long time, it returns to a state without living stars, but not to its beginning. The early dark universe was young, hot in its background, filled with gas that had not yet collapsed into the first galaxies. The future dark universe is old, cold, and full of remnants. The first darkness was before creation. The later darkness is after exhaustion. That difference matters. Because the future universe will contain the records of everything that happened, but in forms almost impossible to read. Heavy elements locked inside cold bodies. Dead planets orbiting dead stars. Black holes containing the mass of countless objects. Photons stretched to enormous wavelengths. Neutrinos passing through space almost undisturbed. Gravitational waves fading across distances that no observer may ever bridge. The universe will not be blank. It will be archived in darkness. But an archive without readers, without light, without accessible signals, is almost the same as forgetting. After the last stars, black holes become the dominant engines. A black hole is often imagined as a violent object, and during the active age of the universe, it can be. Gas falling into a black hole can form a brilliant accretion disk. Friction, magnetic fields, and gravitational energy can heat that disk until it shines brighter than entire galaxies. Jets can fire from near the poles at enormous speeds. Quasars, some of the brightest objects in the universe, are powered by supermassive black holes feeding on surrounding matter. But black holes do not remain brilliant if they run out of fuel. A black hole alone in space is dark. It has mass, it has gravity, it curves space-time. But without matter falling into it, it does not blaze like a star. It waits. In the far future, black holes will still exist after most other luminous objects have faded. Stellar mass black holes will orbit through the remains of galaxies. Supermassive black holes will sit at galactic centers, some grown through mergers into enormous gravitational wells. If galaxies have merged, their central black holes may also merge, releasing gravitational waves that ripple through space-time. For a long age, black holes may be the last major structures with concentrated mass. They are not alive, but they are persistent. They are not shining, but they are present. They are not creative in the way stars are, but they can still shape the motion of anything that comes near them. Eventually, however, even black holes are not expected to last forever. This is where the future becomes speculative, not because the physics is careless, but because the timescales are so enormous and the conditions so far beyond direct experiment. According to the idea of Hawking radiation, black holes should slowly emit radiation due to quantum effects near their horizons. For large astrophysical black holes, this radiation is incredibly weak. A black hole with the mass of a star would radiate so little that it is currently colder than the cosmic microwave background. Today, such a black hole absorbs more energy from the universe around it than it loses. But the universe keeps expanding. The cosmic microwave background keeps cooling. Given enough time, the background temperature falls below the effective temperature of black holes. When that happens, black holes no longer gain more from the surrounding radiation than they lose. Their evaporation, unbelievably slow, becomes the direction of the future. Small black holes evaporate faster than large ones. Large black holes can last for times so long that ordinary language fails. A supermassive black hole may survive for something like 10 to the power of 100 years, depending on its mass. That is not simply longer than human history. It is longer than the lifespan of stars, longer than the age of galaxies, longer than almost any timescale our minds naturally evolved to understand. A number like that does not feel like time. It feels like a wall, and yet the equations treat it as an interval. During the black hole era, the universe is not completely inactive. Black holes can still merge if their orbits bring them together. Remnants can still fall inward. Rare interactions can still happen. But as expansion continues and objects become more isolated, even these events thin out. The universe becomes a place where almost everything that can happen has either already happened or has become too unlikely to matter, except across absurd durations. This is perhaps the deepest meaning of a dying cosmos. Not that time stops, not that matter disappears in one instant, but that change becomes starved. The universe continues, but its ability to produce novelty fades. A star is a machine for transformation. It turns hydrogen into helium, and later, in massive stars, into heavier elements. It creates light. It drives weather on planets. It powers biospheres. It shapes chemistry. It gives time a visible arrow because energy flows outward from a hot center into colder space. A black dwarf does not do that. A cold planet does not do that. A lonely black hole barely does that, except through incredibly faint radiation over almost meaningless spans. The future still has physics, but it loses drama. And when the last black holes evaporate, if Hawking radiation is correct and no unknown process prevents their final disappearance, the universe enters an even deeper quiet. What remains then? Photons, neutrinos, perhaps electrons and positrons, perhaps dark matter particles depending on what dark matter truly is and whether they decay. Perhaps a thin background of gravitational waves. Perhaps particles we do not yet know how to describe. There may be no stars, no galaxies as we understand them, no planets with warm surfaces, no nebulae, no active stellar engines, and no black holes left to anchor large masses. Only diluted energy spread across expanding space. This is the condition often associated with heat death. The phrase sounds dramatic, but the idea is precise in a broad thermodynamic sense. Heat death does not mean everything becomes hot. It means usable energy differences have been erased. Work requires contrast. A heat engine works because one place is hotter than another. Life works because energy flows through systems far from equilibrium. Stars shine because gravity creates dense, hot cores that radiate into colder space. If everything becomes too evenly spread, if no useful gradients remain, then processes that depend on energy flow can no longer continue. The universe may still exist, but it would be unable to do very much. That is why heat death is more frightening than a sudden explosion. An explosion is an event. Heat death is the absence of events. It is not a cosmic fire consuming everything. It is the end of fire as a meaningful process. It is not a final scream. It is the loss of every mechanism that could make a scream, hear it, or remember it. There is another layer to the far future that makes the picture even more unsettling, because not every object waits quietly for heat death in the same way. Some remnants may still find ways to collide. A pair of brown dwarfs, too small to sustain long-term hydrogen fusion, could drift together after an ancient gravitational encounter and merge into something more massive. If the combined object crosses the threshold needed for fusion, then a star could briefly be born in a universe that has almost stopped making them by ordinary means. It would not be a return to cosmic youth. It would be more like a spark struck from old stones. White dwarfs may also have rare futures. Two of them might spiral inward if they orbit close enough and lose energy through gravitational waves. If their combined mass becomes too great, the result could be a thermonuclear explosion, a Type Ia supernova, lighting up an otherwise ancient galaxy with a sudden flash. Or a white dwarf might slowly gather matter from a companion remnant until it crosses a dangerous limit. In the active universe, such explosions help astronomers measure cosmic expansion. In the remote future, they would be rare flashes in a tired dark. Even black dwarfs, if they eventually exist, might not remain completely uneventful in every model. Over staggering periods, quantum effects could alter matter in ways we cannot test directly today. If protons decay, then ordinary matter itself is not forever. A cold remnant made of atoms would very slowly dissolve from within, as the particles inside its nuclei transform into lighter products. If protons are stable, then solid remnants could persist far longer, changing mainly through gravitational encounters, quantum tunneling, and the slow rearrangement of matter under extreme time. This is where the future becomes a map with uncertain roads. We know stars exhaust fuel, We know galaxies age. We know expansion changes what can remain visible. But at the farthest edges of time, we run into questions our experiments have not yet answered. Does the proton decay? What is dark matter made of? Is dark energy truly constant? Can space-time itself change phase? Does quantum gravity modify the fate of black holes? Are there processes so rare that they only matter after numbers of years too large to fit into ordinary imagination? The honest cosmic future contains known trends and unknown doors. That uncertainty does not make the dying less real. It makes the ending less like a single final scene and more like a landscape of possible silences. One path leads toward heat death, where expansion continues and usable energy differences fade. Another, more speculative path could involve a big rip if dark energy grows stronger with time, eventually tearing apart galaxies, stars, planets, molecules, and perhaps atoms themselves. A different path, also dependent on the nature of dark energy, could slow expansion or even reverse it into contraction, though this is not the simplest reading of current evidence. A vacuum transition, if our vacuum state is not the lowest possible state, could rewrite physics in a bubble expanding at nearly the speed of light. But that belongs to the realm of deep theoretical possibility, rather than expected history. The most important thing for this video is not to pretend that every final detail is settled. The important thing is to notice the direction we can already measure. The universe has changed from a hot, dense beginning into a cooler, expanded state. It passed through a peak era of star production. Its galaxies are becoming less fertile on average. Dark energy is pushing unbound regions apart. Long-lived stars will outlast bright ones. Remnants will become more common than living suns. The night that waits at the far end is supported not by one dramatic prediction, but by many connected pieces of physics. That is why the phrase "already dying" is so powerful. It does not mean the universe has no future. It means the future is not an endless repetition of the present. The sky we know is not the default condition of reality. It is a temporary arrangement inside a much longer cooling story. Consider the cosmic microwave background. Today, it fills the universe with a temperature of about 2.7 Kelvin, a faint afterglow from the time when the first atoms formed, and light could finally travel freely. It is already cold, but it will become colder as space expands. Its photons stretch to longer wavelengths, carrying less energy. In the far future, the background will be so diluted and redshifted that detecting it may become nearly impossible for any observer built from ordinary matter. That is not just a technical inconvenience. It changes what a future civilization could know. The cosmic microwave background is one of the strongest pieces of evidence that the universe began hot and dense. Remove that signal from practical observation, remove distant galaxies beyond the horizon, remove most active star formation, and the universe becomes harder to decode. The past does not disappear from reality, but it disappears from accessible measurement. Science depends on evidence arriving. The future universe may contain truths that no local observer can retrieve. This is an uncomfortable idea, because we often think of knowledge as something that simply increases with time. On Earth, later generations can inherit books, data, instruments, and theories. But the universe does not preserve every clue forever. Cosmic expansion can erase access. Stellar death can remove laboratories. Cooling can silence processes. What is obvious in one era can become hidden in another. We may be early enough to see the fossil light of the Big Bang. We may be late enough to understand galaxies, planets, chemistry, and life. That combination is rare in the full timeline. If intelligent observers become more common around long-lived red dwarfs in the remote future, they may have more time, but less universe to see. They might build patient telescopes over millions of years and still find the sky beyond their local group nearly empty. They might develop deep physics from local observations, but the grand historical evidence we use today could be faint, absent, or ambiguous. This possibility makes our era feel less ordinary. We live while the universe is still telling on itself. The evidence of its youth is still crossing the sky. The ruins of its early violence are still visible. The distant galaxies have not all slipped away. The background radiation has not cooled into practical invisibility. The stars have not all become embers. There is also a physical loneliness built into this future. In the present universe, galaxies form clusters, filaments, and walls separated by vast voids. Gravity binds some structures together, while expansion stretches the spaces between unbound structures. In the far future, our local gravitational island may remain, perhaps as a merged galaxy descended from the Milky Way, Andromeda, and nearby companions. But beyond that island, the rest of the observable universe may recede beyond contact. Imagine living in that island. Your telescopes show stars, remnants, perhaps old planets, and a halo of dark matter. But the wider cosmic web has faded from view. The great structure of the universe, which we can map today across billions of light years, has become a story without direct witnesses. That is not the destruction of space. It is the growth of separation. A universe can die by becoming too far apart for its own parts to speak. Communication depends on signals. Signals move at finite speed. If expansion carries regions apart so that future light from one can never reach the other, then those regions no longer share a practical future. They remain part of the same universe in a broad sense, but not part of one another's observable reality. The universe becomes less like a single illuminated city and more like islands drifting over a dark ocean that keeps widening. Each island may keep its own history for a while. Each may have remnants, planets, possible observers, and old records. But the bridges are made of light, and expansion can stretch those bridges until no new crossing is possible. This is why cosmic death has several meanings at once. There is stellar death, when stars exhaust fuel. There is galactic death, when galaxies lose the cold gas needed for starbirth. There is observational death, when evidence moves beyond horizons. There is thermodynamic death, when usable energy differences fade. There may be particle death, if matter itself is unstable. And there is relational death, when distant regions of the universe no longer meaningfully interact. The word death is imperfect for physics, but it captures something real. A system can continue existing while losing the processes that made it dynamic. A galaxy without star formation still has stars and remnants, but its creative phase has ended. A universe without energy gradients may still contain particles, but the ability to build complex, working structures would be gone. This makes the far future almost impossible to visualize with ordinary images. Our imagination loves objects: a planet, a star, a galaxy, a black hole. But heat death is not an object. It is a condition. It is what remains when the differences that make events possible have been spent. How do you picture a universe where almost nothing happens? A black screen is too simple. Darkness alone is not enough. The terrifying part is duration. Not darkness for a night, not silence for a century, not an empty region between stars, but a future so long that the entire age of stars becomes a brief opening chapter by comparison. The bright universe may be a short season. The dark universe may be the climate that follows. And still, that future grows out of the same laws that gave us everything. This is why the topic should not be treated as only depressing. It is also one of the clearest ways to understand how precious cosmic activity is. A star is not just a light in the sky. It is a temporary pocket of low-entropy fuel being converted into radiation. A galaxy is not just a beautiful spiral. It is a structure where gas, gravity, turbulence, radiation, and dark matter briefly cooperate to make generations of stars. A planet like Earth is not just a rock. It is a place where energy from a star flows through atmosphere, ocean, geology, and biology before escaping into space. Life depends on the universe not being finished. It depends on imbalance. It depends on sunlight arriving from a hot star and leaving as cooler infrared radiation. It depends on chemical gradients inside cells. It depends on a planet still geologically and atmospherically active enough to maintain conditions that are neither frozen forever nor boiled away. Heat death is frightening because it is the imagined condition where such flows no longer exist in useful form. No sunlight over oceans. No warm interiors driving chemistry. No fresh stars turning gas into dawn. No concentrated fuel waiting to be spent. Only the aftermath of all spending. That is the future the dying universe points toward, if the simplest long-term picture is correct. But before that future, there will be unimaginable chapters. The Milky Way and Andromeda will merge. The Sun will become a white dwarf. The last human traces on Earth may vanish long before the last stars fade. Red dwarfs may host planets for trillions of years. Dead stars will orbit inside darkened galaxies. Black holes will swallow what falls too close. The cosmic background will cool toward invisibility. Local islands of matter will become separated from the larger universe. Then, across timescales almost beyond mathematics, the final luminous events will become rare accidents. A collision here, a merger there, a faint burst from an evaporating black hole, a last rearrangement in a universe no longer building new systems. The story becomes less about objects and more about probability. Given enough time, even rare events can happen. Given enough expansion, even nearby possibilities can become unreachable. Given enough cooling, even warm remnants become dark. This is why the future is both empty and not empty. There may be particles everywhere, but too spread out to form familiar worlds. There may be radiation everywhere, but too cold to power life. There may be space everywhere, but too little connection to make a shared cosmic story. And when we bring the scale back to ourselves, the contrast is almost painful. A human life lasts less than a blink compared with a star. A star lasts less than a blink compared with the age of black holes. The age of black holes may be less than a blink compared with whatever emptiness follows. Yet our brief moment is the one in which the universe can be known by us. That does not make us central. It makes us temporary witnesses. And witnessing matters precisely because the witnesses do not last. And still, we have to be careful. Cosmology is not finished. Dark energy may not be a simple constant. New observations continue to test whether it changes over time. Dark matter remains unidentified. Quantum gravity is incomplete. Proton decay, if it exists, has not been observed. The true final fate of the universe depends on physics we may not fully understand. There are possible alternatives. If dark energy changes, the expansion history could differ from the simplest picture. If the vacuum of space is not perfectly stable, a vacuum decay event could in principle change the laws of physics in a spreading bubble, though this remains speculative and not something expected on human timescales. If gravity and quantum mechanics combine in a surprising way, black hole evaporation may not end as the simplest models suggest. If the universe has properties beyond the observable region that we cannot measure, its global fate could be stranger than our local evidence implies. So the honest answer is not that we know every final detail. The honest answer is that many lines of current evidence point toward a universe that expands, cools, forms fewer stars, isolates its galaxies, and gradually loses accessible sources of free energy. That is enough to make the title true in a meaningful way. The universe is already dying, not because a countdown clock has appeared in the sky, but because the processes that make it bright have passed their peak. We are living after cosmic noon, not at midnight, not yet, but after the brightest morning. That image is more accurate than a simple apocalypse. The universe is not collapsing around us. The stars are not about to go out tomorrow. Earth still receives sunlight. Galaxies still collide. Nebulae still glow. New stars still form in places where enough cold gas remains. But the direction is visible. Look at the universe as a whole, and the pattern is not youth. It is aging. The surprise is that we can see it. We can measure star formation across cosmic history. We can compare young galaxies with old galaxies. We can detect the expansion of space. We can trace the cosmic microwave background back to a time before stars. We can observe white dwarfs, neutron stars, black holes, red dwarfs, galaxy clusters, and voids. We can place ourselves in the timeline instead of imagining that our era is ordinary. Our era is not ordinary. It is unusually informative. The sky still contains the past. The future will not always be so generous. There is a kind of responsibility in that. Not a moral command written into the stars, but a scientific opportunity. We exist during a period when the universe can be studied deeply. The evidence has not yet faded beyond horizons. The cosmic microwave background is still detectable. Distant galaxies are still visible. Stars still reveal how matter evolves. Planets still form. Life has had time to become conscious, at least here, and consciousness has had time to build instruments. That combination may be temporary. The universe does not owe observers a complete record. It simply happens that we arrived while much of the record can still be read. There is one more way to think about this slow ending, and it begins with a simple question. What would count as a memory in a dying universe? On Earth, memory can be written in books, carved into stone, stored in machines, or carried inside living brains. In astronomy, memory is stranger. The universe remembers through light in transit, through chemical abundances, through orbits, through background radiation, through craters on old surfaces, through the metals inside stars, and through the arrangement of galaxies across space. A dying universe slowly damages every one of those archives. Light travels away. Surfaces erode, collide, freeze, or break apart. Stars that contain chemical records become remnants. Galaxies merge until old structures are mixed together. Expansion carries external evidence beyond reach. Black holes hide information behind horizons in ways that still challenge physics. Even the atoms that make up the records may not be eternal, depending on the deep stability of matter. So the future is not only colder, it is less readable. This is a strange thought, because the past feels fixed. The Big Bang happened, the first stars formed, galaxies assembled, Earth cooled, life appeared, and observers eventually looked outward. Those things do not become false, because evidence fades. But for any future observer, truth and reachable evidence are not the same. A fact can be real and still become impossible to prove from inside a late universe. That is why our moment has acquired urgency. We are not just watching stars before they die. We are watching records before they become inaccessible. Every deep-field image is a rescue of ancient light. Every measurement of the cosmic microwave background is a reading of a message that will not remain equally clear forever. Every map of galaxy clusters captures a structure that dark energy may one day hide from future skies. Every spectrum of an old star preserves a clue about earlier generations that no longer exist. This makes astronomy feel almost like archaeology conducted before the ruins are buried. Except the ruins are not buried under soil. They are buried under time, expansion, cooling, and distance. And that returns us to the emotional center of the video. The dying universe is frightening not because it is loud, but because it is patient. It does not need to chase anything. It simply waits for fuel to run down, for radiation to stretch, for distances to grow, for remnants to cool, and for rare events to become rarer still. A catastrophe can be resisted. A law of nature can only be understood. That may be why this topic feels heavier than ordinary danger. A storm passes, an impact ends, a supernova fades. But entropy is not an event moving through space. It is a direction built into the behavior of energy. It is the reason heat flows from hot to cold. It is the reason stars cannot burn the same fuel twice. It is the reason every glowing thing is also a spending thing. The universe is magnificent because it has produced structure despite that direction. It is terrifying because the direction has never gone away. This changes the emotional meaning of cosmic death. It is not only about loss far in the future. It is about the preciousness of the present. The light we see tonight is not permanent. The Milky Way is not permanent. The sun is not permanent. Even the great black holes are not necessarily permanent. The structures that seem eternal are phases. A galaxy is a phase. A star is a phase. A planet with oceans is a phase. A biological world is a phase. A civilization able to ask these questions is an even narrower phase. And yet phases are not meaningless because they end. In physics, a phase can shape everything that follows. The first stars were temporary, but they made heavy elements. Massive stars died quickly, but their deaths seeded the gas that formed later planets. The sun will not last forever, but its temporary stability allowed Earth to develop oceans, life, and minds. A human lifetime is brief, but inside it, the universe can become aware of itself in a small and fragile way. The dying universe is terrifying because it tells us that no structure gets to keep its form forever. But it is also clarifying. It strips away the illusion that permanence is required for importance. The universe creates through temporary arrangements. Stars hold themselves together for a while. Atoms gather into worlds for a while. Worlds support oceans for a while. Oceans support chemistry for a while. Chemistry becomes life for a while. Life becomes memory for a while. Memory becomes science for a while. And science looks back across the whole chain, not to escape the ending, but to understand where we are inside it. This is why the death of the universe is not just a story about far future darkness. It is the frame around every sunrise, every star, every living thing, and every signal crossing space. The fact that the universe is dying does not make the present empty. It makes the present rare. For now, stars still burn. For now, galaxies still show us their ancient light. For now, the cosmic background still whispers from the early universe. For now, matter is still organized into worlds, atmospheres, oceans, cells, eyes, telescopes, and minds. For now, the universe has not finished spending its inheritance, but it is spending it, slowly, quietly. Every second, the hydrogen inside stars becomes helium. The cold gas inside galaxies becomes rarer. The brightest stars end quickly. The dark energy-driven expansion carries distant galaxies farther away. White dwarfs cool. Black holes wait. The future grows longer than the past by such an enormous margin that nearly all cosmic time may belong not to brightness, but to afterglow. And this is the unsettling truth at the center of it all. We do not live in a universe moving toward greater and greater light forever. We live in a universe where light is a temporary achievement, a flame held up against expansion, a brief order drawn from gravity, gas, and time, a luminous chapter between two darknesses. Before the first stars, the universe was dark because structure had not yet awakened. After the last stars, it may be dark because structure has finally run out of ways to shine. We are between those two nights. That is why the stars matter. That is why galaxies matter. That is why the faint light from billions of years ago matters. Because it is not guaranteed. It is not the default state of reality. It is a temporary rebellion against the cold spread of energy. When you look at the night sky, you are not just seeing distant suns. You are seeing active resistance against equilibrium. You are seeing matter gathered tightly enough to burn. You are seeing gravity win local battles against expansion. At least for a while, you are seeing the universe doing work. Someday, most of that work will be finished. The sky will not simply look different. The physical possibilities beneath the sky will be different. There may be no new Earths forming around young yellow stars, no bright spiral arms full of blue clusters, no nearby galaxies still sending rich histories across space, no cosmic dawn left to observe. Only remnants, radiation, and distances too large to cross. That is the terrifying part. Not that the universe hates life, not that darkness is evil, not that the future is angry. It is that the universe does not need to preserve the conditions that made us possible. Those conditions appeared because physics allowed them for a time. They will fade because physics also allows fading, and the same laws that build stars also let them die. The same expansion that gave the universe room to form structure also helps carry structures apart. The same thermodynamics that lets energy flow through living systems also points toward a future where useful flows become harder to find. Creation and death are not separate rules. They are two sides of the same rulebook. A star exists because gravity compresses gas and fusion releases energy. A star dies because fuel is finite and radiation escapes. A galaxy forms because matter clumps. A galaxy ages because its gas is used, heated, and lost. A universe becomes bright because conditions allow stars. A universe becomes dark because those conditions are temporary. So when we say the universe is already dying, we are not saying the universe is over. We are saying the ending is built into the process from the beginning. The first star that ever ignited was already spending a limited supply. The first galaxy that ever formed was already beginning a long transformation. The first planet that ever cooled was already entering a story shaped by loss, change, and finite energy. And yet, because of those temporary processes, everything interesting became possible. Without stars dying, there would be no heavy elements. Without heavy elements, there would be no rocky planets. Without rocky planets, perhaps no oceans like ours. Without oceans, perhaps no chemistry complex enough to become life. The universe is dying, but it has also used its dying to create. That is why the story is not simple despair. It is stranger. The same cosmic aging that guarantees the lights will one day go out also made it possible for there to be lights in the first place. We are made from a universe that spends itself. Carbon, oxygen, nitrogen, iron, calcium, phosphorus, all of it was shaped by stellar processes that could not last forever. We are not outside cosmic death, watching it from a safe distance. We are one of the temporary arrangements it produced along the way. That makes the ending personal, but not in the way a disaster movie is personal. It is not about a threat arriving at our door tomorrow. It is about the deep structure of existence. Everything organized is temporary. Everything warm cools, unless something keeps warming it. Everything shining is losing energy. Everything living depends on a flow that cannot be frozen in place. This is why the universe can be beautiful and terrifying at the same time. The beauty is not separate from the fragility. The fragility is part of the beauty. A star matters because it burns against the dark. A planet matters because it holds conditions together against chaos. A living world matters because it is not guaranteed by the laws of nature. It is permitted briefly by them. And a mind matters because it can notice. It can look at a sky full of stars and realize that those stars are temporary. It can understand that the oldest light is fading, the newest stars are fewer, and the farthest galaxies are slipping away. It can feel fear and still keep looking. Maybe that is the most human part of the story. We cannot stop the universe from aging. We cannot refuel every star. We cannot pull distant galaxies back across accelerating space. We cannot make the cosmic background young again. But we can understand the direction. We can name the processes. We can measure the light before it vanishes. We can preserve a small part of a cosmic record in memory, science, art, and the machines we send into the dark. That does not defeat heat death. It does not cancel dark energy. It does not make stars immortal. But it means the universe does not pass completely unnoticed. For a brief moment, matter arranged itself into observers. For a brief moment, the dying universe knew enough to ask what dying means. And maybe that is the quiet answer hidden inside this terrifying topic. The universe is already dying. The peak of star formation is behind it. Galaxies are aging. The supply of cold gas is declining. Dark energy is widening the gaps. Stars will end. Remnants will cool. Black holes may eventually fade. The long future points toward a darkness almost impossible to imagine. But right now, the story is not finished. Right now, the sky is still readable. Right now, the sun still shines over Earth. Right now, galaxies still carry their ancient light into our telescopes. Right now, the universe is old enough to be understood, but not so old that understanding has become impossible. That may be one of the rarest positions any observer could occupy. Not at the beginning, when there were no stars. Not at the end, when there may be no new light. But here, in the luminous middle, where the evidence still surrounds us. The death of the universe is not only a future event, it is the slow background of everything we see. It is present in every star that burns fuel. It is present in every galaxy that runs out of gas. It is present in every photon stretched by expansion. It is present in every ancient remnant cooling silently through space. And still, against all of that, the universe glows. Not forever, not everywhere, not with the same strength it once had, but enough for planets, enough for oceans, enough for life, enough for eyes to open under one ordinary star and wonder how long the lights can last. And now we know the answer, not forever in the literal sense, but long enough for the question to be asked, long enough for the evidence to be gathered, long enough for a small world to look into the dark and understand that the darkness is not empty. It is the future, and the stars, for now, are the temporary answer.